Alright, in this video we are going to cover confidence interval for the mean for sample for small sample. As you know, sample we differentiate as the large sample and small sample. The up to 30 you consider as a small sample. Beyond of 30 you consider as a large sample. How about 30 itself? Obviously, since it's on the border, you can use either large sample or small sample. It should be the same. Okay, so for the large sample, we used the z-score table. Remember, but for the For the small sample, we will use t-distribution table. So this t-distribution table you can find in the file where table is. So I would recommend to put on the pause this recording, open your t-distribution table, get ready so you can move on with the video. So if we need to construct confidence interval for the sample size less than 30 and it's a normal distribution, obviously all of it we consider as a normal distribution, and sigma is unknown, then we are going to use t-distribution. So let's see. For t-distribution, we need to know the value of t. There are two ways. So one, how we are going to use this t-distribution, just the same way as we did in the z-score distribution. So we will calculate our t-distribution through this formula. And then we'll take t-distribution from the table, and then we compare. Okay, so how we are going to calculate our t-distribution? X bar is our mean, sample mean, obviously. Mu is our population mean. S is a standard deviation for sample. And N is a sample size. So X minus mu over S over square root of N. So just like in the case of z-score, we're trying to find z-critical, so differentiate where is the error, z-critical, negative z-critical and positive z-critical. Exactly same way we're going to deal with t, negative t-critical and positive t-critical. Okay, it has the same meaning, so it will differentiate the confidence interval from the errors. Those are errors. Okay, but we are going to figure out different way from a t-score table. So what do we need for t-score table? We need degree of freedom. Degree of freedom, we always will find sample size less 1. Okay, sample size less 1. That's the formula for the degree of freedom, because degree of freedom always has to be less than sample size. Y minus 1, just like in the formula of standard deviation, remember we put minus 1. So it would be clear that at least subset at least has to be less by 1 from set. That's why we put n minus 1. So we would know it's less by 1 at least. Okay, So what we're gonna do, we need to find, we are going to find, hold on. Okay. We need to find example here. Find the critical value for 95% confidence level. So if I draw it, use your imagination. It's supposed to be bell-shaped distribution. Okay. And it is going to be 95%. That means we will have a small error. This will be our 95% confidence level. And this small t-score is going to be negative t critical, positive t critical. That's going to be tail. For the sample size is equal 15. So let's see how we are going to figure it out. Here we have, hold on, I want to clean this. So we can use it. So for 95% confidence level, when sample size is 15, we are going to have degree of freedom n minus 1, which will be 15 minus 1 will be equal 14. Now here you see the table T distribution. Maybe on your table, you won't have level of confidence or one tail or two tails, but it doesn't matter. If you have one, you can figure out the rest. Let's say if you have only two tails, okay, 20%, for example, here 20%, then confidence level will be 80%. If you have two tail only 5%, then confidence interval will be 95%. Okay. The other example, there are some tables that give you, for example, only one tail. If they give you one tail 10%, that means you can calculate if one tail is 0.1, then two tails will be times 2, which will be 0.2. And confidence interval will be 1 minus 0.2, which will be 0.8. If one of these three is given, the rest you can figure it out with no big deal. Another example, 0.025. Let's say it's given only one tail, 0.025. For two tails, you'll find out by multiplying by 2, because remember, left tail, right tail, errors are identical. So you will get 0.05. So that's a two-tail error. And confidence at the level of confidence, it's going to be 1 minus 0.05, which will be 0.95. Are we clear? Okay, let me clean this. And now let's get going. So our degree of freedom is 14. And we have 95% confidence level. So confidence level is given here, 95%. And if degree of freedom is 14, so it's going to be what? 2.145, right? Let's see. Opa, it went down to 14. And 0.95, 2.145, T critical. So for left critical will be, T critical will be plus minus 2.145 for positive and negative. Okay. Let's do another example. Let me ask you for another example. Make sure we understand it well. Let me clean all this. So let's assume we want to know one tail is given 0 point, our one tail error, let's take our confidence interval or confidence level is, for example, 99%, okay, and n is equal 30, which means degree of freedom, it's going to be equal 29, right, minus 1, and the confidence level is 99. Here it is, confidence level of confidence, 99. And here is n minus 9 is 29. So if I come here and here, 2.756. T critical is equal to 2.756. One more example. Okay, so let's assume we have a confidence level, for example, 80%, and sample size is 14. So if sample size is 14, that means degree of freedom will be 13, right? Right here. If the confidence level is 80, that means 0.8. So an intersect will be 1.350, which means T critical is equal 1.350. Okay. All right. Moving to next example. So here it's showing 95% with n is 14. It's negative 2.145. That's an example we looked here. Let me see. So 95 and 14. So 2.145. Okay. This is what it's showing here, plus minus 2.145. So what about confidence interval? What is the formula? It's exactly same formula, x bar minus e, x bar plus e. That's where our mu is located. Why do we use it? Because sometimes our population, be it all dolphins in the world, be all children in the world, or birds or animals or people, and we want to find out the average. Obviously, we can never figure out exact average, correct? But by sampling and considering error, so we find out the average of the sample, which is x bar, and figuring out error. Okay. That's not what I wanted. And figuring out the error. So we can approximately figure out in what interval will be our average of the population. Okay. It can be at the end, this end, low boundary, upper boundary, or anywhere in that interval. All we can know that the average of the population, the mean of the population, somewhere in that interval. That's all. So the formula for this case is, for error, is T critical S over square root of N. You remember the formula for error for Z score? The error for the larger population, it was the same way. Instead of T critical, we used Z critical. Instead of S, which is standard deviation of sample, we use standard deviation of the population. Remember? So it's identical, it's just we are using the standard deviation of table and standard deviation of the sample. And instead of z-score of the z-score for large sample, we are using t-score for smaller sample. Okay? So again, I'm skipping these instructions. I don't want a blunt reading here. You can read itself, but I would rather show all these instructions based on example. So what do we have here? We randomly select 16 coffee shops and measure temperature of the coffee sold at each. 16 coffee shops. What is going to be 16 coffee shops? Of course, it's going to be sample size, right? The sample mean, keyword sample mean, which is mean X bar, temperature is 162 degrees Fahrenheit. With sample standard deviation, which is going to be S, is equal 10 degree of Fahrenheit. Find the 95% confidence interval. So our confidence interval is 95%. Okay, 95% for the population mean temperature. So we need to find confidence interval, how much it will make, that interval. So it's given 95%, but we need to convert this percentage into value. What interval it's going to make is 95%. Assume temperatures are approximately normal distribution. We always can use these formulas for normal distributed area. All right, so let's see how we're going to solve it. So our n is less than 30, obviously. And sigma is not known. Sigma was standard deviation of the population. Is not known. Instead, is known standard deviation of the sample. So what we're gonna do, therefore, it's a small sample size. Sigma is not known, is unknown. Therefore, we can use our t-score table. So to find t critical, why do we need to find critical? Because we need to find our mu that is going to be greater equal x bar with minus error less equal x bar plus error, correct? That's what we need to know. Since our x bar is given already, all we need is find error. Okay, formula for error was t critical s over square root of n. So s we have it, there we go. N we have it, 16. All we need is find out t critical. So open your t critical, your t critical table or t distribution table. It's the same thing. So for n is equal 16, which means degree of freedom will be 15, right? Degree of freedom, 15. And standard, it's at confidence interval 95, 0.95. See how much will give you t critical. And let's see, you should get, oh, okay, we have here also. Let me clean this. So it's going to be 2.131. Let's understand. 95. Here is 95. 0.95. And degree of freedom is going to be 15. Therefore, it's going to be 2.131, our t critical. Okay? So once we have t critical, we can easily find out error, correct? So that's 5.3. All right? So once we have 5.3, we can find out the end points. boundaries, which is going to be x minus error, x plus error, 162 minus 5.3, 162 plus 5.3, and we will get this interval. Here we go. This is our interval, and this is point of estimate, x bar, and the average of the mu, average of the population is somewhere between 156.7, 167.3, which means with 95% confidence you can say the population mean temperature of coffee that is sold is between 156.7 degrees and 167.3 degrees. Okay, that's how approximately we figure out how hot the coffee is at the sales point. This is just the table, everything we learned. I'll just go, I can go over real quick. I don't think you are going to go that deeply, but I would like to explain to you one more time real quick. So the bottom line is everything starts to how to identify when to use normal, which is z-score, z-distribution, when to use t-distribution. If n is greater or equal 30, which is yes, then we are using z-score. And that is when sigma is unknown. And when if sigma unknown, we use S. Actually, you can forget about this saying. All you want to do, use E distribution. I mean, the z-score distribution, and use this formula. That's it. If sigma is not given, which means standard deviation of population is not given, you can use S. So it's going to be either sigma or S, doesn't matter. So that's when greater than 30. So if greater than 30, no wondering, no doubt, you jump and do the z-score calculation for error. If it's less than 30, so you are going to look if population is normal distributed, then you use t-distribution because it's less than. But it can be less than, let's say it can be n is equal 20, less than, but sigma would be known, and sigma known, which is population standard deviation. If it's less than 30, but population standard deviation is given, then you still successfully use z-score calculation and error. But if, let's say, n is 20, and sigma, which is the population standard deviation, is unknown, I would rather put there not known, because it will be better. Not known. Is not known, then you are using t-critical. So one more time, when sample size is less than 30, then it can be either z-score or t-score. If sigma, standard deviation of population, is given, then you still successfully using the z-critical. So if sigma is not known with a small sample size, then you use t-critical. All right? This is your algorithm how to figure out when you use z-score, z-critical, when you use t-critical. So let's figure it out here. It says normal or t-distribution. You randomly select 25 new constructed houses. So n is 25. The sample mean x bar is 181,000. And the population standard deviation, so this is not S, This is sigma. Okay, is 28,000. Now remember, if sample size is less than 30, but sigma is given, what do we use, t-score or z-score? Of course we are going to use z-score, which means we are going to use z-score, normal z-score distribution. Let's see. Okay. So use normal distribution table. Why? Because this is the most important part. Population standard deviation is given. Okay, very good. Next one. Oh, it doesn't give you any example anymore. Well, okay, that's all. Obviously, we are done. So it's pretty easy. On MyMathLab, I believe the questions are explained pretty well. So if you have any questions, please contact me right away. Okie dokie.